close your eyes for a moment. Now just imagine you're standing in absolute darkness, but not the darkness of at night, where your eyes eventually adjust and you begin to make out the faint silhouettes of furniture, but true, absolute darkness. The kind of darkness that exists in deep caves tons of miles beneath the Earth's surface, even where no photon of light has traveled in millions of years. And now, imagine you're holding a lantern. When you light it, something extraordinary happens. That flame doesn't just appear. It sends messengers racing outward in every possible direction. These messengers are photons, tiny packets of light energy, and they're moving at a speed so incomprehensible that your own human mind struggles to grasp it. They're traveling at 299,792,458 meters per second. That's roughly 186,282 miles per second, if you prefer. It's the speed you can't even image. But these numbers, as precise as they are, don't quite capture the reality of what's happening. In the single second it takes you to say the word light, these photons from your lantern could travel around the Earth's equator 7.5 times. In that same second, they could journey from New York to Sydney and back again 14 times over. They move so quickly that if you could travel at light speed, you could reach the moon, that pale disk that's watched over humanity since we first looked up at the night sky, in just over 1 second. But here's where it becomes truly profound, truly humbling. The universe is so vast, so incomprehensibly enormous, that even traveling at this impossible speed, the fastest speed that anything in our universe can achieve, it takes light years to cross even relatively short cosmic distances. The light from the nearest star beyond our sun, a small red dwarf called Proxima Centauri, takes 4 years and 4 months to reach us. The light you see from it tonight left that distant star when you were 4 years younger. You're not seeing it as it is now. You're seeing its past, preserved in photons that have been traveling through the void for longer than most presidential terms. This is what tonight's journey is about. We're going to explore the distances of space not in miles or kilometers. Those units become almost meaningless at cosmic scales, but in the time it takes light to travel. We'll measure the universe the way the universe measures itself, in light years, light hours, light minutes, and light seconds. And as we drift through this exploration together, as your breathing slows and your muscles relax, you'll begin to understand something profound about our place in this cosmos. We are creatures of a tiny planet, orbiting an average star, in an unremarkable region of a galaxy that is itself just one of hundreds of billions. But we are also made of atoms forged in the hearts of dying stars, capable of understanding our own cosmic insignificance, capable of measuring the immeasurable, capable of grasping, however imperfectly, the true scale of existence. So settle in, get comfortable, let the darkness of your room become the darkness of space, and let's begin our journey outward, riding on beams of light, measuring the vast distances that separate us from everything else in the universe. The journey begins with a single photon. Let's follow it. ###. What is the speed of light? Before we can understand the distances light travels, we need to understand the light itself. So let's start with something simple, something happening right now, all around you. Light is reaching your eyes at this very moment. If you're listening in a darkened room, perhaps there's a faint glow from a device screen, or moonlight filtering through a window, or the distant sodium orange glow of streetlights. Each photon that reaches you has made a journey, however brief. But what exactly is this photon that we keep mentioning? Think of a photon as a quantum of light, the smallest possible packet of electromagnetic energy. It has no mass, yet it carries energy. It behaves sometimes like a wave rippling through space, and sometimes like a particle striking surfaces with measurable impact. This dual nature puzzled physicists for centuries, and in many ways it still does. Light refuses to be entirely one thing or another. It exists in a state of quantum ambiguity, being both until we force it to be one. When you turn on a light, you're not creating light, you're releasing energy that was stored in chemical bonds or electrical potential, and that energy transforms into electromagnetic radiation. Some of that radiation falls within the narrow band of frequencies that our eyes evolved to detect. We call this visible light, though it's just a tiny sliver of the electromagnetic spectrum, bookended by infrared on one side and ultraviolet on the other. Now, here's the truly remarkable thing about light. In a vacuum, in the empty space between stars, between galaxies, in the vast cosmic voids where matter is so sparse that you might find only a handful of atoms per cubic meter, All light travels at exactly the same speed regardless of its wavelength or frequency. A photon of red light, with its long, lazy wavelength, travels at exactly the same speed as a photon of blue light, with its shorter, more energetic oscillation. Both move at 299,702,458 meters per second. We usually round this to 300,000 kilometers per second, or about 186,000 miles per second, but the precision matters to physicists because this number is fundamental to how our universe works. In fact, the speed of light isn't just a speed limit for light, it's the speed limit for causality itself, for cause and effect, for information, for any influence traveling from one point to another. Nothing with mass can reach this speed. Nothing can exceed it. It is, as far as we know, the universe's ultimate speed limit, written into the very fabric of space-time. Why this particular speed? Why not faster? Why not slower? The answer lies in the nature of space and time themselves. Light speed isn't arbitrary. It emerges from the fundamental properties of the electromagnetic field and the structure of space-time. When James Clerk Maxwell first wrote down his equations of electromagnetism in the 1860s, they predicted that electromagnetic waves would propagate at a specific speed, and when he calculated that speed, he found it matched the measured speed of light. This was no coincidence. Light is an electromagnetic wave, and its speed is determined by two fundamental constants, the permittivity and permeability of free space. But let's bring this back to something more tangible, something we can visualize as we drift towards sleep. Imagine a photon being born in the tungsten filament of an old incandescent light bulb. An electron, excited by the electrical current, drops to a lower energy state, and in that quantum leap it releases a photon. That photon emerges from the filament and begins its journey. It crosses the glass envelope of the bulb in about a billionth of a second, so quickly that the bulb might as well not be there at all. It travels through the air of your room, bouncing off walls, being absorbed and re-emitted by the paint, scattering off dust particles floating in the air currents. This journey through matter slows it down slightly. Light travels marginally slower through air than through vacuum, and much slower through glass or water. But if that photon could escape into space, if it could leave the atmosphere and find itself in the vacuum between worlds, it would accelerate to its maximum speed, that universal constant, 299,792,458 meters per second. At this speed, our photon could circle the Earth's equator 7.48 times in a single second. If you were standing at the equator and could somehow throw a ball at light speed, you can't but bear with the thought experiment. It would lap the Earth and hit you in the back of the head 7.48 times before you even finished your throwing motion. In 1 second, traveling at light speed, you could go from New York to Los Angeles and back again 25 times. You could travel from the Earth to the Moon and back, twice with time to spare. You could reach any point on Earth's surface from any other point in less than a 20th of a second. These comparisons, while staggering, are still somewhat graspable, because they reference distances we understand, places we've been or at least seen photographs of. But light's true journey, its cosmic journey, doesn't begin until it leaves Earth behind entirely. So let's follow our photon as it escapes Earth's gravity well and heads out into the solar system. Let's see what distances really mean when measured by the universe's ultimate speed, our cosmic neighborhood. Our photon leaves Earth, traveling upward, though up loses meaning quickly in space, away from the surface, through the exosphere where the atmosphere gradually merges with the vacuum of space, past the satellites that orbit our planet in their various shells, from low Earth orbit at a few hundred kilometers to geostationary orbit at 35,786 kilometers. At light speed, it takes our photon only 0.12 seconds to cross geostationary orbit. The satellites there, which appear to hover over a fixed point on Earth's surface because their orbital period matches our planet's rotation, are already far behind. The Moon appears ahead, our only natural satellite, our companion in space, the object that stabilizes Earth's axial tilt and gives us our regular seasons. It's been a constant presence in human imagination for as long as we've had imagination. Ancient cultures worshipped it, poets have written about it, lovers have walked beneath it. In 1969, humans first set foot on its dusty, airless surface, one of our species' greatest achievements. The Moon orbits Earth at an average distance of 384,400 kilometers. That's roughly 238,855 miles. It seems immensely far when you consider that the Wright brothers' first flight covered only 37 meters, or that the International Space Station orbits at a mere 400 kilometers altitude. But to our photon traveling at light speed, the moon is close, remarkably close. The journey from Earth to moon takes our photon exactly 1.28 seconds, less time than it takes to say one Mississippi to Mississippi. When you look up at the full moon on a clear night, the light entering your eyes left the lunar surface just over 1 second ago. You're seeing the moon not as it is, but as it was 1.28 seconds in the past. This delay is so brief that it's irrelevant for any practical purpose. The moon hasn't changed meaningfully in that second. It's still there, in almost exactly the same position, reflecting the same sunlight. But this small delay introduces us to a profound concept. The farther we look into space, the farther we look back in time. Light, for all its incredible speed, still takes time to travel. And space is so vast that these travel times stretch from seconds to minutes to years to millions and billions of years. Let's continue our journey outward. Past the moon, space becomes truly empty. The occasional atom of hydrogen drifts in the darkness, left over from the solar nebula that formed our planetary system 4.6 billion years ago. A stray particle of cosmic dust, perhaps. Silicate minerals blown out from Mars by ancient asteroid impacts, or complex organic molecules from comets that periodically sweep through the inner solar system. Our photon continues, and ahead lies the sun. Not ahead in the sense that our photon is traveling toward it, but ahead in our narrative, as we measure distances out from Earth. The sun, that vast sphere of incandescent plasma, that fusion reactor that has burned steadily for 4.6 billion years and will continue burning for another 5 billion, sits at the center of our solar system. Its mass is 333,000 times that of Earth. Its volume could contain 1.3 million Earths. Every second it converts 600 million tons of hydrogen into helium through nuclear fusion, releasing energy in the process, energy that eventually becomes the light warming our planet, powering our photosynthesis, driving our weather, making life possible. The distance from Earth to the Sun varies because Earth's orbit isn't a perfect circle. It's an ellipse. At perihelion, when we're closest, we're about 147 million kilometers from the Sun. At aphelion, when we're farthest, we're about 152 million kilometers away. On average, we orbit at about 150 million kilometers from our star. This distance is so useful for measuring cosmic scales that astronomers gave it a name, 1 astronomical unit, abbreviated as 1 AU. It's the yardstick of the solar system, the unit we use to measure distances to planets and asteroids and comets. But even this immense distance, 150 million kilometers, even this gulf that no human has ever crossed, is not so vast to light. Light from the sun's surface reaches Earth in approximately 8 minutes and 20 seconds. Think about what this means. When you step outside on a sunny morning and feel the warmth on your face, that warmth left the sun's surface over 8 minutes ago. The light entering your eyes right now, illuminating the world around you, began its journey before you stepped outside. If the sun were to suddenly vanish, instantly, impossibly, in violation of all laws of physics, we wouldn't know for 8 minutes and 20 seconds. The sky would remain bright, the day would seem normal, and then, 500 seconds after the event, the world would plunge into darkness and deadly cold. This is our first real glimpse of what cosmic distances mean. 8 minutes doesn't sound like much. You might spend 8 minutes making coffee or showering or waiting for a bus, but to travel the distance light covers in those 8 minutes, even in our fastest spacecraft traveling at tens of thousands of kilometers per hour, would take months, years for most of our probes. Voyager 1 and Voyager 2, launched in 1977, are humanity's most distant ambassadors. They visited Jupiter and Saturn, sending back stunning images of those giant worlds and their moons. Voyager 2 continued on to Uranus and Neptune, the only spacecraft ever to visit those distant ice giants. After completing their planetary missions, both Voyagers continued outward, and they're still traveling, still sending back data, more than 4 decades after their launch. They're moving at about 17 kilometers per second relative to the Sun, incredibly fast by human standards. At that speed, you could travel from New York to Los Angeles in less than 4 minutes. But Voyager 1, the more distant of the two, is currently about 24 billion kilometers from Earth. In light travel time, that's about 22 light hours. It takes 22 hours for a radio signal from Earth to reach Voyager 1, and another 22 hours for Voyager's response to reach us. A round-trip conversation takes nearly 2 days. In more than 40 years of travel, moving at 17 kilometers per second, Voyager 1 has covered a distance that light crosses in less than 1 day. This tells us something profound about the scale of space, even within our own solar system. The distances are so vast that even light, the fastest thing in the universe, takes hours to cross them. And our spacecraft, our fastest vehicles, traveling at a tiny fraction of light speed, take decades to traverse what light crosses in hours. Voyager 1 has left the heliosphere, the bubble of solar wind that surrounds our sun. It's officially in interstellar space now, the space between the stars, though it's still gravitationally bound to the sun and will remain so for tens of thousands of years as it coasts outward through the Oort cloud, that distant shell of icy comets. But here's the humbling part. Voyager 1 won't reach the distance of the nearest star, Proxima Centauri, for about 70,000 years, and that star is considered our close neighbour in cosmic terms. The solar system, as vast as it is just our front yard. The real distances, the distances that make even light's journey measurable in years rather than minutes, begin when we venture beyond the sun's gravitational influence, out into the dark between the stars. But before we take that leap, let's understand the tool we'll use to measure these greater distances. The light year. To no man territory, introduction to the light year numbers can be deceptive. They can lull us into thinking we understand something when really we're just manipulating symbols. Consider the number 1 million. You can say it easily, 1 million. You can write it 1 million. But do you really grasp what a million is? If you started counting right now, one number per second, without stopping to sleep or eat, it would take you 11.5 days to reach 1 million. A million seconds is about 11.5 days. A million minutes is nearly 2 years. A million hours is 114 years, longer than any human has ever lived. Now consider 1 billion. In modern American and British usage, a billion is 1,000 millions, 1 billion. If you counted one number per second, it would take you 31.7 years to reach 1 billion. A billion seconds ago, it was 1991. A billion minutes ago, the Roman Empire still existed. A billion hours ago, humans hadn't yet evolved. These numbers start to lose meaning. They become abstract, disconnected from our lived experience. We can say billion, or trillion, or quadrillion, but these are just sounds, just symbols on a page. They don't create comprehension. This is the problem astronomers faced when trying to communicate cosmic distances. The distances between stars, between galaxies, between clusters of galaxies are so enormous that expressing them in familiar units like kilometers or miles produces numbers that are essentially meaningless. The distance to the nearest star beyond our sun, Proxima Centauri, is about 40 trillion kilometers. That's 40 trillion kilometers. Written out, it looks impressive, but what does it mean? Can you visualize that distance? Can you compare it to anything in your experience? Of course not. The number is too large to grasp intuitively, so astronomers needed a new unit, a unit that was appropriate to cosmic scales, a unit that captured something meaningful about the nature of space and the speed of light. They chose to measure distance by time, specifically by the time it takes light to travel. A light year is the distance that light, traveling at 299,792,458 meters per second in vacuum, covers in 1 Julian year, exactly 365.25 days. When you calculate this out, 1 light year equals approximately 9.46 trillion kilometers, or about 5.88 trillion miles. Still an incomprehensible number, you might think. And you're right, it is. But here's the elegant part. We don't have to comprehend the number. We just have to understand the concept. When an astronomer says a star is 4 light years away, they're not asking you to visualize 37.8 trillion kilometers. They're telling you something much more intuitive. The light you see from that star tonight left the star 4 years ago. You're looking 4 years into the past. If that star exploded in a supernova 3 years ago, you wouldn't know yet. The light from the explosion is still traveling toward you, and it won't arrive for another year. This is the beauty of the light year as a unit. It does 2 things simultaneously. It tells you how far away something is, and it tells you how far back in time you're looking when you observe it. Let's ground this with some examples from our cosmic neighborhood, starting close to home and working outward. The Sun, as we mentioned, is about 80 light minutes away. We're looking 8 minutes into the past when we see it. Jupiter, the largest planet in our solar system, orbits at an average distance of about 5.2 astronomical universe from the Sun. Light takes about 43 minutes to travel from the Sun to Jupiter. When you look at Jupiter through a telescope, you're seeing it as it was between 32 and 52 minutes ago, depending on where Earth and Jupiter are in their respective orbits. Neptune, the most distant of the 8 major planets, orbits at about 38 AN/UC from the Sun. Light takes about 4 hours and 10 minutes to reach Neptune from the Sun. The Hubble Space Telescope images of Neptune that have awed us over the years show Neptune as it was 4 hours in the past. Pluto, though no longer classified as a major planet, orbits at an average distance of about 39.5 astronomical. Light takes about 5.5 hours to reach Pluto from the Sun. When New Horizons flew past Pluto in July 2015, giving us our first close-up images of that distant world, the radio signals carrying those images took 4.5 hours to reach Earth from the spacecraft. Mission controllers sent commands and then waited 9 hours for confirmation that the commands had been received and executed. 4.5 hours for the signal to get there, 4.5 hours for the response to come back. At the outer edge of the Kuiper Belt, that region of icy bodies beyond Neptune's orbit, we're at about 50 ATUs from the Sun, which is about 7.5 light hours. This is still within our solar system, still under the Sun's gravitational influence, but we're now dealing with light hours rather than light minutes. The scattered disk, a region of space where objects have highly elliptical orbits that take them far beyond the Kuiper Belt, extends to about 100 ASTRA-Union, or roughly 14 light hours. Sedna, one of the most distant objects we've discovered in the solar system, has an orbit that takes it as far as 937 ATIU from the Sun at its most distant point, about 5.4 light days away. And beyond that lies the Oort cloud. The Oort cloud is a theoretical shell of icy bodies surrounding the solar system, extending from about 2,000 astronomical strikers to as far as 100,000 astronomical strikers from the Sun. We've never directly observed the Oort cloud. Individual objects there are too small and too far away to see with our telescopes. But we infer its existence from the long-period comets that occasionally fall into the inner solar system, their orbits suggesting they originated from a vast, distant reservoir of icy material. The inner edge of the Oort cloud is about 2,000 ASTRI away, which is about 0.03 light-years. Light takes about 11 days to travel from the Sun to the inner Oort cloud. The outer edge at 100,000 HWU is about 1.6 light-years away. Light takes a year and 7 months to reach the outer Oort cloud. This is where we transition from thinking in terms of our solar system to thinking in terms of interstellar space. The Oort cloud is the final frontier of the Sun's gravitational dominance, the last echo of our star's influence. Beyond it lies the true vastness of space, the gulf between stars, distances so great that we must measure them in light-years, not light hours or light days. And this is where our journey truly begins. This is where we leave behind the familiar, the explored, the places where human-made objects have travelled, and venture into distances that challenge not just our technology but our imagination, our sense of place, our understanding of what it means to be a small, fragile species on a small, fragile planet, looking out into an incomprehensibly vast cosmos. As you lie here, comfortable and warm, perhaps feeling the first gentle pull of sleep beginning to loosen your grip on waking consciousness, consider this. The nearest star to our Sun is 4.24 light-years away. If you could travel at light speed, which you can't but imagine it, you would journey for 4 years and 3 months before reaching it. Every human who has ever lived, every civilization that has ever risen and fallen, every story that has ever been told, every dream that has ever been dreamed, has occurred within a bubble of space-time that light crosses in 1.6 years, the diameter of the Oort cloud. Beyond that, for 4 years in any direction, no stars, no planets, no matter at all except perhaps a few stray atoms per cubic meter, wandering hydrogen molecules lost in the dark. We live in a profound isolation. Our nearest neighbour is 4 years away at the speed of light, unreachable by any technology we possess or can imagine possessing in the near future. And yet, when we look up at the night sky, we see thousands of stars, each one a sun like ours, each one perhaps surrounded by planets of its own, each one separated from us by years of light travel time. The light entering your eyes from those stars left them long ago, 4 years ago, 10 years ago, hundreds of years ago, thousands of years ago. The sky is an archive of the past, a cosmic history book written in starlight. Some of the stars you can see with your naked eye have already died. Their light continues traveling toward us, will continue traveling for years or centuries more, but the stars themselves have exhausted their nuclear fuel, collapsed, perhaps exploded in supernovae, leaving behind only neutron stars or black holes. We're seeing ghosts, echoes of stars that no longer exist. This is what distance means in the universe. This is what light years measure. Not just space, but time. Not just how far, but how long ago. As we continue our journey in the next section, we'll travel outward from our solar system, visiting nearby stars, exploring our galactic neighborhood, understanding what it means to live in a spiral arm of the Milky Way galaxy, contemplating the 100,000 light-year diameter of our galactic home. But for now, rest with this thought. You are lying on a planet that orbits a star, and that star is just one of hundreds of billions in a galaxy that is itself just one of hundreds of billions in the observable universe. The distances between these objects are so vast that even light, the fastest thing that exists, the universal messenger, the carrier of information and causality, takes years, millennia, millions and billions of years to cross them. You are infinitesimally small in a cosmos that is incomprehensibly large. And yet you are here, conscious, able to contemplate these distances, able to understand, however imperfectly, your place in the vastness. There is something profound in that. Something worth sitting with as sleep approaches, as your breathing deepens, as the boundaries between waking and dreaming begin to blur. The universe is vast, but you are part of it. You are made of atoms forged in dying stars, scattered across space, eventually coalescing into planets and life and consciousness. You are the universe observing itself, measuring itself, wondering at itself. And that, perhaps, is the most remarkable distance of all. Not the distance between stars, but the distance the universe had to travel to become aware of its own existence. From the first photons released in the Big Bang to the photons entering your eyes right now, carrying information about distant worlds, the universe has been on a journey of self-discovery that spans billions of light years and billions of years of time. You are a part of that journey, a small part perhaps, but an essential one. And now, as we prepare to continue our exploration, as we ready ourselves to venture farther into the cosmic distances, let yourself rest. Let the vastness wash over you, let the numbers and the scales and the light years become a gentle backdrop to your thoughts, a cosmic lullaby that speaks of distances so great they become almost meaningless, and in that meaninglessness, somehow, find a strange comfort. The universe is vast, you are small, and yet here you are, contemplating it all, connected to everything by the simple fact of your existence, your consciousness, your ability to wonder. Rest now. There are more light years to explore, more distances to contemplate, more wonders to discover. But they can wait. They've been waiting for billions of years already. They'll wait a little longer while you sleep. The stars are patient. The light is always traveling. And we'll continue our journey soon. For now, let the darkness embrace you. Let the quiet settle in, and know that you're exactly where you're supposed to be. Here, now. A conscious being in an ancient and enormous cosmos, resting before the next leg of a journey that spans the observable universe. The cosmos will be here when you wake, the nearest star systems, Proxima Centauri. Let your breathing slow. Feel the weight of your body against whatever surface supports you. We're about to take a journey across a distance that no human has ever crossed, that no human spacecraft will cross in our lifetimes, that represents a gulf so vast it redefines what we mean by the word distance. We're going to visit our nearest stellar neighbour. Imagine standing on Earth at night, looking up at the southern sky. If you're in the southern hemisphere, in Australia, South Africa, South America, you can see a constellation called Centaurus, the Centaur. It's one of the largest constellations in the sky, rich with stars, and within it lies something extraordinary. A triple star system called Alpha Centauri. To the naked eye, Alpha Centauri appears as a single bright star, the third brightest star in Earth's night sky. But it's actually 3 stars bound together by gravity, orbiting their common center of mass in an eternal cosmic dance. 2 of these stars, Alpha Centauri A and Alpha Centauri B, are similar to our Sun, Yellow and orange dwarf stars, burning hydrogen in their cores through nuclear fusion, stable and steady. They orbit each other every 80 years, sometimes drawing as close as the distance between our Sun and Saturn, sometimes separating to the distance between our Sun and Pluto. If you stood on a planet orbiting one of these stars, you would see two suns in your sky, one bright and warm, the other dimmer but still brilliant, both casting double shadows, creating a world where the concept of day and night would be forever complicated. But it's the third member of this system that holds a special place in human imagination and scientific interest: Proxima Centauri. Proxima is a red dwarf, a small star, much smaller and cooler than our Sun. If our Sun were the size of a basketball, Proxima Centauri would be the size of a ping-pong ball. It has only about 12% of the Sun's mass and emits only 0.17% of the Sun's luminosity. If you somehow replaced our Sun with Proxima Centauri, Earth would freeze solid within days. The tiny star's feeble light wouldn't be enough to warm our world. But Proxima Centauri is special for one simple reason. It is the closest star to our solar system. The distance from our Sun to Proxima Centauri is 4.24 light-years. Let that sink in for a moment, 4.24 light-years. Light travelling at 290,792 kilometers per second takes 4 years and 88 days to cross the distance between our Sun and the nearest star beyond it. In more familiar units, this distance is about 40.2 trillion kilometers or 25 trillion miles. These numbers are so large they become abstract, meaningless. So instead, let's think about what this distance means in practical terms. If you could travel at the speed of Voyager 1, humanity's fastest spacecraft, moving at about 17 kilometers per second, it would take you approximately 75,000 years to reach Proxima Centauri. That's roughly the entire span of time that modern humans have existed as a species. All of recorded human history is only about 5,000 years. It would take 15 times the length of all recorded history to make this journey at our current technological capabilities, even if we could build a spacecraft that travelled at 1% of the speed of light, a speed that would require technology far beyond anything we currently possess, technology that would require solving problems of energy generation and propulsion that seem almost insurmountable. The journey would still take 424 years. No one alive at launch would survive to see the destination. It would be a multi-generational voyage, a ship that would become a world unto itself, carrying a small population of humans who would live and die in the darkness between stars. This is what 4.24 light-years means. This is the distance to our nearest neighbour. And yet, in cosmic terms, Proxima Centauri is practically touching us. It's right next door. It's in our stellar neighbourhood, our cosmic cul-de-sac. The vast majority of stars in our galaxy are much, much farther away. In recent years, Proxima Centauri has become even more interesting to us because we've discovered that it has planets. In 2016, astronomers confirmed the existence of Proxima Centauri b, a planet with at least 1.17 times Earth's mass, orbiting in what might be the star's habitable zone, the region where liquid water could exist on a planet's surface. Imagine that. Just over 4 light-years away, there might be a world with oceans, with clouds, with weather patterns, with geology. Whether that world has life, we don't know. Probably we won't know in our lifetimes. But the possibility exists right there, closer to us than any other star system. The light you would see if you stood on Proxima Centauri b would be dimmer and redder than the light we receive from our Sun. The star would appear about 3 times larger in the sky than our Sun appears from Earth, but it would cast a deep red glow over everything, like a perpetual sunset. If the planet has an atmosphere, its sky might be a strange colour, perhaps purple or deep blue depending on the atmospheric composition and how it scatters the red dwarf's light. And if you looked up from Proxima Centauri b, searching for Earth, you would need a telescope. You could find our Sun. It would be a bright star in your sky, visible to the naked eye, appearing in the constellation Cassiopeia from that vantage point. But you wouldn't be able to see Earth itself. You'd be looking at the Sun as it was 4.24 years ago, seeing ancient light, observing the past. This is the reality of interstellar distances. Even at the scale of a few light-years, we are profoundly separated from other star systems. The idea of interstellar travel, so common in science fiction, faces obstacles that aren't just technological but fundamental. The distances are so vast and the speed of light is such an absolute limit that even communication becomes challenging. If we sent a radio message to Proxima Centauri today, It would take 4.24 years to get there. If there was someone there to receive it and respond immediately, we wouldn't get their reply for another 4.24 years. A single exchange of messages would take 8.48 years. You could ask a question when you were 20 years old and receive the answer when you were nearly 30. Let's continue our survey of nearby stars. Beyond Proxima Centauri and its two brighter companions, the next nearest star system is Barnard's star, a red dwarf about 5.96 light-years away. After that comes Lumen 16, a binary system of brown dwarfs, objects that are larger than planets, but not quite massive enough to sustain hydrogen fusion and become true stars. At 659 light-years, Y08550714, a sub-brown dwarf so cool that water clouds might exist in its atmosphere, lies about 7.2 light-years away. Wolf 359, another red dwarf, is 7.86 light-years distant. Lalande 21185, yet another red dwarf, sits 8.29 light-years away. Do you notice a pattern here? Most of our nearest stellar neighbours are red dwarfs, small, cool, dim stars. This isn't a coincidence. Red dwarfs are by far the most common type of star in the galaxy, making up about 70.75% of all stars. They're the galactic norm. Stars like our Sun, yellow G-type main sequence stars, are actually somewhat uncommon, and larger, brighter stars are rarer still. Sirius, the brightest star in Earth's night sky, is 8.6 light-years away. It's actually a binary system consisting of Sirius A, a brilliant white main sequence star twice as massive as our Sun, and Sirius B, a white dwarf, the collapsed core of a star that has exhausted its nuclear fuel. Sirius appears so bright in our sky not because it's particularly close, though 8.6 light-years is nearby in cosmic terms, but because Sirius A is intrinsically very luminous, about 25 times more luminous than our Sun. Ross 154, Epsilon Eridani, Lacaille 9300. Ross 128, EZ Aquarii, Procyon, 61 Cygni Strove, 2398, Groombridge 34 Epsilon Indi. These names might be unfamiliar to you, might sound like catalogue designations rather than the poetic names given to brighter, more famous stars. And that's exactly what they are. These are the stars that surround us, our true neighbours, and most of them are too dim to see with the naked eye. Most of them are red dwarfs, invisible without telescopes, quietly burning their hydrogen fuel so slowly that they'll outlive our Sun by trillions of years. Within a sphere of 12 light-years centered on our Sun, there are approximately 30 known star systems, containing a total of about 50 individual stars and brown dwarfs. This is our immediate stellar neighborhood, our local vicinity, and it's surprisingly sparse. The average distance between stars in this region is about 5 light-years. Think about that. On average, stars near the Sun are separated by gaps, but light takes 5 years to cross. 5 years of travel at the universe's ultimate speed limit, just to reach the next point of light. As you extend the radius further, to 50 light-years, you encompass approximately 2,000 star systems. To 100 light-years, you include perhaps 15,000 star systems. The volume of space grows with the cube of the radius, so as you look farther out, the number of stars increases dramatically. But even at 100 light-years, a distance that light takes a century to traverse, we're still in a very small corner of the galaxy. We're still in the immediate suburbs of our spiral arm, still in the Orion Spur, that minor branch of the Milky Way spiral structure where our solar system happens to reside. The galaxy, as we're about to explore, is vastly larger than this. The distances we've discussed so far, a few light-years, a few dozen light-years, even 100 light-years, are barely noticeable on the scale of the Milky Way. They're like measuring the distance between houses on a street when the city itself stretches for thousands of miles. But before we zoom out to that larger scale, rest with this thought. The nearest star to our Sun is more than 4 years away at light speed. The stars you can see with your naked eye on a clear night, those bright points of light that have guided travellers and inspired poets for all of human history, are mostly within a few hundred light-years of us. The farthest individual star you can see with the naked eye, Deneb in the constellation Cygnus, is about 2,600 light-years away. The light entering your eyes from Deneb left that star around 600 BCE, when the ancient Greeks were establishing their city-states and the Buddha was teaching in India. Every photon that reaches you from these distant stars has been travelling through the void for years, decades, centuries, millennia. Each photon is a messenger from the past, a quantum of energy that has crossed unimaginable distances to end its journey in your eye, to be absorbed by the photoreceptor cells in your retina, to be converted into a neural signal, to become part of your conscious experience of looking up at the night sky, by information traveling at the universe's maximum speed. And that light tells you not just where these stars are, but when they were, years ago, centuries ago, existing in a past that is their present but your history. This is the strange reality of living in a universe where light has a finite speed, and distances are measured in the time it takes light to travel. The farther you look, the farther back in time you see. Your vision is a time machine, and the universe is an archive. As you drift deeper into relaxation, into that space between waking and sleeping, let yourself sit with the profound isolation of stars, separated by such vast gulfs of space that even light, the fastest messenger, takes years to carry information from one to another. And yet, despite this isolation, here we are, products of stars made of star stuff, as Carl Sagan famously said, contemplating the stars that made us, measuring the distances between us and them, understanding our place in a cosmos that is both incomprehensibly vast and intimately connected, the vastness of the Milky Way. Let's pull back now. Let's rise above the scale of individual nearby stars and see our galaxy as a whole. Let's understand the true scope of the Milky Way, the island universe that is our home. On a clear, dark night, far from city lights, you can see a band of diffuse light stretching across the sky. Ancient cultures around the world noticed this band and gave it various names. The Greeks called it Galaxias Kyklos, the Milky Circle, from which we get our word galaxy. Norse mythology described it as the road to Valhalla. Hindu cosmology saw it as the Akash Ganga, the river of light. Aboriginal Australians saw it as a river in the sky where a celestial canoe travels. What you're seeing when you look at the Milky Way is our galaxy viewed from inside. You're seeing the combined light of hundreds of billions of stars, so distant that they blur together into a cloudy band. You're looking through the disk of the galaxy, seeing deeper concentrations of stars, observing the galactic plane edge on because we're embedded within it. The Milky Way is a barred spiral galaxy. Imagine a disk like an incredibly vast dinner plate, with a central bulge and spiral arms curving out from the center. The disk is about 100,000 light-years in diameter. That is, light takes 100,000 years to cross from one edge to the other. The disk is relatively thin compared to its width, only about 1,000 light-years thick in most places, though the central bulge is much thicker, perhaps 10,000 light-years from top to bottom. 100,000 light-years. We've been talking about distances of a few light-years to our nearest stars. Now we're contemplating a structure that is 100,000 light-years across. The scale has jumped by a factor of 20,000 or more. The distances within our galaxy dwarf the distances between nearby stars in the same way that the distances between stars dwarf the distances within our solar system. Let's try to grasp this scale through comparison. If our sun were the size of a grain of sand, 1 millimeter across, Proxima Centauri would be another grain of sand about 30 kilometers away. The entire galaxy, on this scale, would be about 700,000 kilometers across, nearly twice the distance from the Earth to the Moon. Alternatively, imagine that the distance from Earth to the Sun, 1 astronomical unit, is represented by 1 inch. On this scale, the distance to Proxima Centauri would be 4.24 miles. The diameter of the Milky Way would be about 6 million miles, roughly the distance the Earth travels around the Sun in about a month. These comparisons still feel abstract. So let's think about it in terms of travel time. A light photon leaving Earth right now would take 100,000 years to reach the opposite edge of the galaxy. By the time it completed that journey, if it could somehow report back to us, it would be describing an Earth from 200,000 years ago, a time when Homo sapiens had only recently emerged as a distinct species, when Neanderthals still lived in Europe, when the last ice age was beginning its cycle. At the speed of Voyager 1, crossing the galaxy would take about 1.7 billion years. That's longer than complex multicellular life has existed on Earth. The Milky Way contains somewhere between 200 and 400 billion stars. The exact number is uncertain because we can't see the entire galaxy. We're embedded within it, and dust and gas block our view of distant regions. But this is the scale. Hundreds of billions of stars, each one a sun, many of them likely surrounded by planets, spread across a disk 100,000 light-years wide. Our solar system is located about 26,000 light-years from the galactic center. We're in the Orion Spur, a minor spiral arm between two major arms called Sagittarius and Perseus. We're in the galactic suburbs, in a relatively quiet region, neither in the crowded center nor in the sparse outer regions. The galactic center itself is a fascinating and violent place. At its very heart lies Sagittarius A, a supermassive black hole with a mass about 4 million times that of our Sun. Stars near the galactic center orbit this black hole at tremendous speeds. Some complete their orbits in only a few decades, moving at thousands of kilometers per second. If our Sun was somehow transported to the inner light year around Sagittarius A, it would be torn apart by tidal forces, its matter drawn into an accretion disk around the black hole, heated to millions of degrees, emitting X-rays and gamma rays before finally crossing the event horizon and vanishing from the universe. The light from the galactic center that reaches us today left there 26,000 years ago, when we observed Sagittarius A with our telescopes, or rather, when we observed the effect of its gravity on nearby stars and gas, as the black hole itself emits no light. We're seeing it as it was in the late Paleolithic, when the last ice age was reaching its peak and early humans were creating cave paintings in France and Spain. The central bulge of the galaxy, that thick region around the core, is densely packed with old stars. These are population 2 stars, formed early in the galaxy's history, metal poor. In astronomical terms, metal means any element heavier than helium, many of them red giants in the late stages of their lives. The average distance between stars in the central bulge might be only 1 light-year or less. Still vast by human standards, but crowded compared to our neighborhood where stars are typically 5 light-years apart. If Earth were located in the central bulge, our night sky would be dramatically different. Instead of a few thousand stars visible to the naked eye, you might see hundreds of thousands. The sky would be so bright with starlight that true darkness might never occur. Multiple bright stars would cast noticeable shadows. The band of the Milky Way would still be visible, but you'd be seeing it from near its center, looking outward, seeing the spiral arms as bright structures arcing across the sky. The spiral arms of the galaxy are regions of higher stellar density, but they're also regions of active star formation. They contain vast clouds of molecular hydrogen, the raw material from which stars form. These clouds, some of them hundreds of light-years across and containing hundreds of thousands of times the mass of our Sun, are collapsing under their own gravity, fragmenting into smaller clumps, each clump heating up as it compresses until eventually, in the densest cores, the temperature and pressure become high enough to ignite nuclear fusion. Our Sun was born in such a cloud, about 4.6 billion years ago. The cloud that gave birth to our solar system also gave birth to thousands of other stars. They've long since drifted apart, scattered across the galaxy by gravitational interactions and their own orbital motions. Somewhere in the galaxy, perhaps 100 light-years away, perhaps thousands of light-years away, there are stars that are our Sun's siblings, born from the same molecular cloud. We don't know which ones they are, we may never know. They've become lost in the crowd of hundreds of billions of stars. The spiral arms are also where you find the most massive stars, blue giants and supergiants that burn through their nuclear fuel in only a few million years before exploding as supernovae. These stars are short-lived by stellar standards, which is why you find them near their birthplaces in the spiral arms. They don't have time to drift far before they die. Our Sun, being an average star with a lifespan of about 10 billion years, has made approximately 20 orbits around the galaxy since it formed. Each orbit takes about 225 to 250 million years, a period sometimes called a galactic year or cosmic year. The last time our solar system was in its current position in its galactic orbit, the Triassic period was beginning on Earth, the supercontinent Pangaea was intact and the first dinosaurs were just emerging. Think about that. Our entire solar system, Sun and planets together, is moving through the galaxy, orbiting the galactic center. We're moving at about 220 kilometers per second relative to the galactic center. That's nearly 500,000 miles per hour. In the time it takes you to read this sentence, we've traveled hundreds of kilometers through space on our orbital path around the galaxy. But because the galaxy is so vast, our motion is imperceptible. The stars around us move similarly, and the patterns of constellations remain essentially unchanged over human lifetimes, over centuries, even over millennia. Only over timescales of tens of thousands of years do the constellations noticeably shift as individual stars follow their own slightly different orbits. Beyond the visible disk of the galaxy, there's a roughly spherical halo of dark matter, mysterious invisible mass that interacts with normal matter only through gravity. We can't see this dark matter, but we know it's there because of its gravitational effects. The visible galaxy we can see, all the stars and gas and dust, makes up only about 0.015% of the galaxy's total mass. The rest is dark matter, and we still don't know what it's made of. There's also a spherical halo of old stars and globular clusters, dense, spherical collections of stars that orbit the galaxy's center. These globular clusters, some containing hundreds of thousands or even millions of stars, packed into a region only a few dozen light-years across, are among the oldest objects in the galaxy, formed not long after the galaxy itself came into being about 13 billion years ago. Within the disk between the spiral arms, there are also darker regions, rifts and clouds of dust and gas that block our view of more distant stars. The Great Rift in the Milky Way, a series of overlapping dust clouds, is visible as a dark band splitting the Milky Way when you view it from a dark site. These aren't empty regions, they're actually filled with matter. But that matter is in the form of dust grains, tiny particles that absorb and scatter light, preventing us from seeing what lies beyond them. The Milky Way is not alone. It's part of a small cluster of galaxies called the Local Group, which contains about 80 galaxies in total. Most of these are dwarf galaxies, small collections of a few billion stars or fewer, gravitationally bound to the larger members of the group. The Milky Way is one of the two dominant members of the Local Group. The other is the Andromeda Galaxy, designated M31, a spiral galaxy somewhat larger than our own, containing perhaps 1 trillion stars, located about 2.5 million light-years away. 2.5 million light-years. We've jumped in scale again, from 100,000 light-years across the Milky Way to 2.5 million light-years, to our nearest large galactic neighbour. The light we see from Andromeda when we observe it with telescopes left that galaxy 2.5 million years ago, before the genus Homo had evolved on Earth, when our distant ancestors were still Australopithecines walking the African savanna. Andromeda is visible to the naked eye under dark skies as a faint fuzzy patch in the constellation Andromeda. It's the most distant object you can see without optical aid, 2.5 million light-years away, and yet faintly visible because it contains so many stars that their combined light crosses that enormous gulf of space and reaches your eyes. Andromeda and the Milky Way are approaching each other, pulled together by their mutual gravitational attraction. In about 4.5 billion years, around the same time our Sun will be nearing the end of its main sequence life, the two galaxies will collide, not a collision of stars. The distances between stars are so vast that even when galaxies merge, individual stars almost never hit each other. But the galaxies will pass through each other, their gravitational interactions disrupting spiral arms, triggering bursts of star formation, eventually merging into a single, larger elliptical galaxy that astronomers have nicknamed Milkomeda. The Local Group also contains the Triangulum Galaxy M33, another spiral galaxy about 2.7 million light-years away, and various dwarf galaxies, the Large and Small Magellanic Clouds, the Sagittarius Dwarf Elliptical Galaxy currently being torn apart and absorbed by the Milky Way, and dozens of others, some discovered only in recent years as our surveys improve. The Local Group occupies a volume of space about 10 million light-years across. Light takes 10 million years to cross from one side to the other, and yet, on the scale of the universe, the Local Group is a tiny structure, a small cluster of galaxies, bound together in an ocean of space that contains hundreds of billions of other galaxies, many of them much, much farther away. As you rest here, contemplating these scales, feeling the gentle pull of sleep, consider what it means to live in a galaxy of hundreds of billions of stars, spread across 100,000 light-years, orbiting slowly around a supermassive black hole, accompanied by a few dozen nearby dwarf galaxies and one large companion galaxy 2.5 million light-years away. The distances are so vast that they lose meaning. The numbers are so large they become abstract. And yet this is our home. This is the Milky Way, the galaxy that contains our Sun, our solar system. Every star you can see in the night sky, every star humans have ever observed without telescopes. We are residents of the Milky Way, citizens of a galactic community so vast that light from one side takes 100,000 years to reach the other. We're part of something enormous, ancient, slowly spinning through the darkness of intergalactic space. One island universe among hundreds of billions, separated from our neighbours by millions of light years of nearly empty void, and yet for all its vastness, the Milky Way is just our immediate cosmic home. The universe extends far beyond it, far beyond even the local group, into distances that begin to challenge not just our technology but our conceptual frameworks, our ability to relate the measurements to anything we can intuitively grasp. Time travel. Looking into the past. There's a sense in which every moment of observation is an act of time travel. When you look at your hand in front of your face, you're not seeing your hand as it is right now in this instant. You're seeing light that left your hand a few nanoseconds ago, billionths of a second. An immeasurably tiny delay, but a delay nonetheless. The photons bouncing off your skin traveled the short distance to your eyes at light speed, taking a tiny fraction of time to complete the journey. You're observing your hand in the very recent past. When you look at someone across the room, you're seeing them as they were a few nanoseconds to a few microseconds ago, depending on the distance. The person you're seeing has already moved on, already changed, already continued existing into the future, while your visual perception is catching up, processing light that left them moments ago. These delays are so small that they're irrelevant for any practical purpose. Your brain doesn't notice. The difference between now and a few nanoseconds ago is meaningless in human experience. But scale this up to cosmic distances, and something profound emerges. The finite speed of light means that looking into space is equivalent to looking back in time. The farther away you look, the farther into the past you see. The universe becomes a vast archive of its own history, preserved in photons travelling across space, carrying information about distant places and ancient times. We've already mentioned this principle in passing, but let's explore it more deeply now, as your mind relaxes and opens to the strange implications of living in a universe where light has a finite speed. When you look at the moon, you see it as it was 1.28 seconds ago. Nothing significant happens to the moon in that time. It's essentially the same object it was a second ago, so this delay doesn't matter. When you look at the sun, you see it as it was 8 minutes and 20 seconds ago. If the sun were to suddenly vanish, impossible, but imagine it. You wouldn't know for 8 minutes and 20 seconds. The Earth would continue in its orbit, the sky would remain bright, and then, more than 8 minutes after the impossible event, darkness and cold would suddenly arrive. When you look at Jupiter through a telescope, you're seeing it as it was between 32 and 52 minutes ago, depending on where Earth and Jupiter are in their respective orbits. The great red spot you observe might have changed slightly in that time. The cloud bands might have shifted. You're observing history, recent history, but history nonetheless. When you look at Proxima Centauri, you're seeing it as it was 4.24 years ago. If Proxima Centauri exploded in a supernova yesterday, which is impossible for a small red dwarf, but imagine it, you wouldn't know for more than 4 years. The star would continue to shine in your sky, looking exactly as it always has, while in reality, it had already destroyed itself. The photons carrying that information would still be traveling toward you, and they wouldn't arrive for years. This becomes more dramatic as we look at more distant stars. Sirius, the brightest star in the night sky, is 8.6 light-years away. When you look at Sirius, you're seeing it as it was 8.6 years ago. The light entering your eyes left that star in late 2015 or early 2016 when the world was different, when you were younger. Vega, a bright blue-white star in the constellation Lyra, is about 25 light-years away. The light you see from Vega tonight left that star in 1999, when the world was preparing for Y2K, when the internet was young, when smartphones didn't exist, when many people reading this hadn't yet been born. Arcturus, a red giant star and one of the brightest stars in the northern sky, is about 37 light-years away. Its light left around 1987, the year of Black Monday, the year Prozac was introduced, the year the world's population reached 5 billion. Betelgeuse, the red supergiant in Orion's shoulder, is approximately 650 light-years away. When you look at Betelgeuse, you're seeing it as it was around 1374 CE, when the 100 Years' War was raging in Europe, when the Ming Dynasty was just beginning in China, when the Black Death had recently ravaged the world. The North Star, Polaris, which has guided travelers for millennia, is about 433 light-years away. Its light left around 1590, when Shakespeare was writing his plays, when Galileo was experimenting with falling objects and pendulums, when the first English colony in the Americas was still years in the future. Deneb, One of the farthest stars visible to the naked eye is about 2,600 light-years away. The light reaching your eyes from Deneb left that star around 600 BCE, when the ancient Greeks were developing philosophy and democracy, when the Buddha was teaching in India, when Confucius was articulating his ethical system in China, when Rome was transitioning from monarchy to republic. Each of these stars is a time capsule. Each photon that reaches you from these distant suns is a messenger from the past, carrying information about what that star was like decades, centuries, millennia ago. But here's where it becomes truly strange. For all we know, some of these stars no longer exist. Betelgeuse, being a supergiant nearing the end of its life, could have exploded in a supernova at any point in the last 650 years, and we wouldn't know yet. The explosion might have happened in 1500, in 1700, in 1900, even last year, and the light from that cataclysmic event would still be travelling toward us. Betelgeuse might be gone, replaced by an expanding cloud of gas and a neutron star or black hole at its core, and yet it still shines in our sky, looking exactly as it always has. This is the strange reality of astronomical observation. We can never see the universe as it is now. We can only see it as it was, recently for nearby objects, anciently for distant ones. The night sky is not a snapshot of the present. It's a layered image of the past, with different layers representing different moments in history, depending on how far away each object is. When we observe galaxies, this effect becomes even more dramatic. The Andromeda Galaxy, as we mentioned, is 2.5 million light-years away. When you observe Andromeda with a telescope, you're seeing it as it was 2.5 million years ago, before modern humans existed, when our ancestors were Australopithecines in Africa. The Triangulum Galaxy, visible as a faint smudge to the naked eye under perfect conditions, is about 2.7 million light-years away. Same story. You're observing a galaxy as it was before humans, before Homo, before much of the genus evolution that led to us. But these are our nearest galactic neighbours. Look beyond the local group, and the distances, and therefore the look-back times, increase dramatically. The Virgo cluster, a large cluster of galaxies that includes the giant elliptical galaxy M87, is about 54 million light-years away. When we observe M87, we're seeing it as it was 54 million years ago, shortly after the non-avian dinosaurs went extinct, when mammals were beginning to dominate terrestrial ecosystems, when the ancestors of horses, elephants, and whales were small, strange creatures that would be barely recognizable as related to their modern descendants. In 2019, the Event Horizon Telescope collaboration released the first direct image of a black hole, or rather, the first image of the shadow cast by a black hole's event horizon, surrounded by an accretion disk of superheated matter. That black hole is at the center of M87, with a mass about 6.5 billion times that of our Sun. The image that made headlines around the world was showing us that black hole as it was 54 million years ago. We're observing deep history preserved in photons that have crossed millions of light-years of space to reach our telescopes. Go farther, and the look-back times extend into the hundreds of millions and billions of years. The Coma cluster of galaxies is about 320 million light-years away. We see it as it was when the first reptiles were evolving on Earth, when the supercontinent Pangaea was beginning to form, when Earth had a single global ocean called Panthalassa. The ellular life had diversified on Earth, when life was still mostly single-celled, when the atmosphere was just beginning to accumulate oxygen. At 2 billion light-years, we're seeing a universe as it was before eukaryotic cells. Cells with nuclei had even evolved. The most distant objects we can observe are nearly at the edge of the observable universe. The light from these objects has been traveling for most of the age of the universe itself. The cosmic microwave background radiation, which we can detect with radio telescopes, is the afterglow of the Big Bang itself. This radiation was emitted when the universe was only 380,000 years old, when it cooled enough for electrons and protons to combine and form neutral hydrogen atoms, allowing light to travel freely through space for the first time. That light has been traveling ever since, and we detect it today as microwave radiation, stretched to longer wavelengths by the expansion of space itself. When we observe the cosmic microwave background, we're seeing the universe as it was 13.8 billion years ago, just 380,000 years after the Big Bang. We're observing the earliest light in the universe, light that has traveled across the entire age and breadth of the observable cosmos to reach us. This is time travel in its most literal sense. We can't travel backward in time ourselves. The laws of physics as we understand them forbid that, but we can observe the past. We can see it, measure it, analyze it, understand it. The universe is a time machine that allows us to look backward, to see how things were billions of years ago, to watch the evolution of galaxies and stars and cosmic structures across vast stretches of time. And here's another strange implication. Somewhere in the universe, 26,000 light-years from Earth in the direction away from the galactic center, there might be astronomers on a planet orbiting another star, looking toward us with their telescopes. They're not seeing our sun as it is today. They're seeing it as it was 26,000 years ago. They're seeing our solar system when early humans were creating the first cave paintings. If there are astronomers on a planet orbiting a star in the Andromeda galaxy, and if they have telescopes powerful enough to observe individual stars in the Milky Way, they're seeing our galaxy as it was 2.5 million years ago. They're observing a Milky Way that existed before humans, before Homo, seeing stars that might have already died but whose deaths haven't reached us yet, missing stars that have been born but whose light hasn't reached them yet. The universe has no universal now. There's no cosmic clock that ticks simultaneously everywhere. Instead, there are countless local nows, separated by light travel time, each observing the other's pasts, each unable to access each other's presents. This is what relativity means on cosmic scales. Time and space are intertwined. Distance and duration become equivalent. Looking out into space is looking back in time, and the deeper you look, the farther back you see, until eventually you reach the limits of observation, the edge not of space but of time itself, the moment when the universe became transparent to light and information could begin traveling across it. As you lie here, feeling the gentle tug of sleep, contemplate this. You are an observer in a universe that preserves its own history and light. Every moment of the past that was bright enough to emit photons still exists somewhere in those photons, traveling outward at light speed, carrying information about what was, spreading that information across the cosmos. The light that left your body moments ago is now meters away, traveling outward. The light that left Earth yesterday is now billions of kilometers away. The light that left Earth when you were born is now decades away in light distance, spreading outward in an expanding sphere, carrying information about Earth as it was on the day you were born. Somewhere, far away, an alien astronomer with a powerful enough telescope could observe Earth as it was on your birth date. They could, in principle, zoom in and see the hospital where you were born, see the people who were there, see the world as it was at that moment. That information exists, encoded in photons, spreading outward forever at the speed of light, a permanent record of the past, traveling through time as well as space. This is the universe we live in, a cosmos where past and present and future are separated not just by time but by space, where the night sky is a vast archive of cosmic history, layer upon layer of light from different distances and therefore different times, all arriving simultaneously at your eyes, creating a composite image that spans billions of years of cosmic evolution. You are looking at history, always. Unavoidably, the present is forever beyond direct observation, accessible only in your immediate vicinity, where light travel time is measured in nanoseconds. Everything else, everything beyond arm's reach, is the past, recent or ancient, depending on the distance. Let it settle into your mind as you settle into sleep. You are a time traveler in the only way the universe allows, by observing light that left distant sources in the past, by looking outward and therefore backward, by understanding that the cosmos you observe is not as it is, but as it was. The universe is vast in space, but it's equally vast in time, and the two are inextricably linked, woven together into the four-dimensional fabric of space-time that Einstein described, where every event has coordinates not just of position but of time, where separation means both distance and duration. Tomorrow night, if you look up at the stars, remember, you're seeing the past. You're observing light that left those stars years ago, decades ago, centuries ago. You're a witness to history, cosmic history, preserved in photons that have crossed the vast gulfs of space to reach your eyes. And somewhere, perhaps, beings on distant worlds are looking at our sun, our galaxy, seeing the light that left us years ago, observing our past while we remain forever hidden in their future, information that hasn't reached them yet, traveling toward them at light speed on a journey that will take years or centuries or millennia to complete. We're all separated by time as much as by space. We're all observing each other's histories. And the present, that razor-thin moment of now, is accessible only locally, only nearby, only within the tiny sphere of space, where light travel time is so brief that the distinction between past and present becomes meaningless. Sleep well, traveler. Dream of light crossing the darkness, of photons carrying information across billions of years, of a universe so vast that even light, the fastest thing that exists, takes eons to cross it. The cosmos is patient, the light is always traveling, and we're here to observe it, to measure it, to understand it, to marvel at the strange and beautiful reality of a universe where distance and time are two aspects of the same thing, where looking far means looking back, where the night sky is history written in starlight. Rest now. There are more wonders to explore, more distances to contemplate, but they can wait. They've been waiting for billions of years already. They'll wait a little longer. The light will keep traveling, the universe will keep expanding, and you'll continue your journey through space-time, a brief spark of consciousness in a cosmos beyond comprehension, understanding just enough to know how little we understand, knowing just enough to be filled with wonder. Sleep well. The stars are waiting. The light is traveling. Tomorrow, the journey continues.